in Montreal. I'm going to be talking about the wired equivalent privacy, or WEP protocol, that's part of the 802.11 wireless Ethernet standard that most of you are probably using right now. Well, you're using the standard, you're not using WEP, because they didn't even bother turning it on here. This is joint work with a couple of my old colleagues at UC Berkeley, where I recently graduated, Nikita Borisov and David Wagner. So, just a brief outline what I'm going to talk about. That's really far away. I'm going to talk about what the WEP protocol is, what it's designed to do, and a brief but pretty technical description. This talk, it's in the more technical session. It's going to be more technical. I can make it as technical as you like, or less technical if you think I'm being too technical. So please give feedback and do this and stuff, or shiny lights in my eyes, or something like this, and I'll pick on you and you'll get to have a say. After I talk about what the WEP protocol is, I'll talk about some attacks against the WEP protocol. I'll talk about the attacks in a couple of broad categories. One is attacks involving key stream reuse, and the second is attacks involving message authentication. Then I'll talk about countermeasures. How can we protect WEP against these attacks? I'll talk about lessons for designing secure protocols that we've learned from the problems with WEP, and then conclude. So, introduction. This is pretty straightforward. Mobile computing is basically getting really, really popular, right? A lot of you in the audience right now have laptops hooked up to wireless Ethernet cards, and it's a really useful thing to do. Recently, there's been a standard basically adopted for wireless Ethernet so that the cards produced by different manufacturers all can talk to each other. And that's great. The great thing about standards is there's so many to choose from. In this case, it's even better because there isn't. Right? We've got one standard, everyone talks it, and so we can talk to each other. This is called the IEEE 802.11 standard for wireless Ethernet. It's gone through a couple of revisions. Currently, most cards implement the 802.11b version. The B basically stands for bigger. No, not really. But it's upped the bit rate of 802.11 from 2 megabits to 11 megabits per second. But the WEP part, the security part, has been the same right from the beginning of 802.11 to now, so I don't need to differentiate between 802.11 and B and whatever. So when we use wireless networking out there, there are some pretty big security issues. The packets are going over the ether, the airwaves, the radio waves, and unlike physical cables, it's really hard to control how far those radio waves get. A lot of companies install 802.11 systems in their buildings, assuming, maybe somewhat naively, maybe they just don't understand what's going on, that the radio waves stop at the building walls, right? It's pretty clear they don't. I mean, how many of you have done more driving or have seen like a bunch of work, right? This is getting a more popular activity. People go around, drive around in cars with 802.11 gear and just pick up on whatever companies have open networks. Turns out if you drive down like Market Street in San Francisco, you can go basically the entire way and never lose 802.11 coverage. That's pretty awesome. So these radio waves can go everywhere, right? So as good IT administrators, what we want to do is keep the bad guys out. As good bad guys, we want to keep the bad guys in, but so we have this conflict. But that's why we're here. So let's say we want to keep people out. How do we keep people from reading traffic, from modifying traffic, from accessing our network when they shouldn't be there? And the answer is the WEP protocol, wired equivalent privacy. And the claim is that the WEP protocol offers the same level of security as a physical wire. right? So if you had a physical wire in your office, the WEP protocol is supposed to provide the same level of security between two wireless nodes in your office that a physical wire between them does, okay? So what are the security goals in particular? The WEP protocol is intended to enforce three main security goals, and these security goals are documented in the 802.11 standard. Not very well, mind you. There's no one place where it says the following are the security goals of the WEP protocol, which is unfortunate because protocol design should have that explicitly written, and that's possibly one of the lessons. But if you look at different sections of it, it says, and here what we're doing is protecting against this, and here what we're doing is protecting against this, and you put them all together, and you find these three security goals come out. The first is confidentiality. You want to prevent the adversary from being able to learn the contents of packets that are traveling over the air, right? This is basically just encryption. The second is access control. You want to prevent an adversary from using your wireless infrastructure. Okay, so you've deployed this wireless network for your building. You don't want to let just some random spammer drive up to your parking lot and dump all this SMTP traffic over your network. And the third is data integrity. This is to prevent an adversary from modifying your data in transit. So you're, say, a bank with a wireless network, and things are going over the wireless net, and even if the adversary can't read it, as in the first point here, if he can modify that data, which you will subsequently accept as authentic, we still have a big problem, right? He can perform all sorts of funny things, either just by scribbling it and causing very strange money transfers to happen, or maybe intentionally just changing a packet so that the dollar value changes, or that his name is substituted in the pay to field of all traffic, right? Though he would be caught pretty quickly for that. So these are the three main security goals. WEP, unfortunately, satisfies none of them. So that's unfortunate. So we're going to talk about how it is that WEP satisfies none of them and what we can do to fix it. But in order to do that, we have to talk about what WEP is. So here's where the tech knob starts twisting up to 7. We'll go higher later. So a brief description of the WEP protocol. The sender and receiver share a secret key, which we'll call K. Right? This secret key in WEP is, there are two versions of WEP. There's the 40-bit version, in which K is 40 bits long, and there's the 128-bit version, in which K is 104 bits long. Okay, I'm not sure where the marketing people came up with that, but they call it 128-bit WEP, but the key is only 104 bits long. Okay, it's just as hard to break 104 as it is to break 128, so really there's no difference. Okay, now let's say the sender wants to transmit a message M to the receiver. Here's what he does. 4 steps. First step is compute a checksum, which I'll denote by C of M, which does not depend on the key K. It only depends on the checksum, on the message. So it's basically a hash of the message. Now we pick an IV, which is initialization vector. It basically means just pick a random number V and generate a key stream using the stream cipher RC4. So I'll talk a bit more about this later, but basically what this means is you have RC4. Does anyone not know what RC4 is? Not heard of it? Awesome. Okay, so you have RC4, which is a stream cipher. It takes as input a key and outputs a key stream. It never takes the message in or anything like that. A stream cipher generates a key stream, which is then XORed against the message to encrypt it, and the same key stream is XORed against the ciphertext to decrypt it. And XORs cancel, so you get the original message back. So this denotation, RC4 bracket V comma K, means you take the random number V and the secret key K, you stick them together to make a bigger string, part of which is random, part of which is the shared secret. Use that bigger string as the key for RC4, and then take the resulting RC4 output. Okay, this is actually a perfectly standard construction with stream ciphers. And we'll see why that this V is necessary. Why don't you just use RC4 of K? I mean, that's a random sequence of bits, both the sender and receiver know it. We'll see why you don't use that in a couple of slides, why the V is important. Okay, and then you just do what you normally do with RC4, which is you take the message, which is now M, and you've stuck the checksum C of M at the end of it. So you have this message which is slightly longer than the original one, and you XOR it against the key stream to get the ciphertext. And then what you transmit over the air is V, the random value, and the ciphertext. Okay? Now the receiver, what does he do? He takes the V that was transmitted over the air, because he doesn't know how to generate V. V was picked randomly or however it was picked, sequentially or something. Could be the same value every time. The spec actually allows you to do that, which is not very clever. And the shared K, to generate the same key stream, RC4 V comma K, you XOR it with the ciphertext, and you get the original message and a checksum back. And then you check that the checksum is in fact the correct checksum on the message. And if it is, you assume that the packet was correctly transmitted, there were no errors, there was no adversary, and that the original sender actually knew the key, and you accept the result as the message transmitted. So we'll draw a little picture here, just so you get it. The CRC is the checksum, so you take the message, you stick the checksum at the end, you take the key stream out of RC4 with V and K as inputs, you XOR the two together to get the ciphertext, and then you stick V at the front and you send it. Okay? Pretty little picture, which is in your notes. Okay, so okay, I've turned mine off too. So WEP uses RC4 as I mentioned, and yeah. Not at all. So WEP assumes that you have a shared secret between two endpoints and doesn't at all talk about how it gets there. In many places where WEP is used, it's simply manual keying. I just type the secret into this computer and into this computer and into this computer. And oftentimes everyone, like at Berkeley, for example, everyone has the same shared secret, right? Two people can keep a secret if one of them is dead, right? Now how about a few thousand people? There are more advanced ways of distributing keys, and people sell products which do better key management, but as we'll see, those products help almost not at all, right? Because key management isn't the problem. Well, it's one problem, but it's not even the problem I'm talking about. You have to solve that one as well. Okay, so they used RC4, which is a well-known stream cipher, which is good. At least they didn't try to make their own cipher, right? I'm sure all of you know of products that, ooh, we've generated our own secret and or patented, although some people, you can't really do secret and patented technology, to make our ultra cool, hyper secure system and, like, say, GSM. And and then somebody finds a flaw in it in 2 hours over an Indian lunch. So yeah, so don't do that. So they were clever, they used RC4. And okay, so I've said how RC4 works. You have a key stream, K, capital K, out that you XOR against the plain text to get the ciphertext, and the receiver just does the XOR again and gets the plain text back, and XORs cancel, and math is in green, and you see that this, okay? You can read it in your books. Okay, so now we're going to come to why we need that V. This is what we call the two-time pad problem. I'm sure most of you are familiar with the one-time pad. The one-time pad is an information theoretically secure cipher. That is, it is impossible to break with any amount of computing power under certain assumptions. And some of the assumptions include that the key is generated, or the key is called the pad, is generated completely randomly using a physical source of randomness, and that the key stream is never reused, right? So two independent bits of pad, two different bits of pad are completely uncorrelated. There are no two bits that have any relationship at all. And you can prove pretty easily that this is completely secure. An adversary seeing a message encrypted with a one-time pad knows basically the length of the message and no other information, right? Now, why is it that we need to never reuse the data, reuse the key stream? Well, if we reuse the key stream, we get what's called a two-time pad. Suppose that plaintexts 1 and 2 are encrypted with the same key stream K. Then the first ciphertext is P1 XOR K, the second ciphertext is P2 XOR K. Now what happens, the adversary, let's say he knows or guesses that these two ciphertexts were encrypted using the same pad. He XORs the ciphertexts together, and the K's cancel out in the XOR. So you just get the XOR of the ciphertext is the same as the XOR of the plaintexts. Now the adversary just has a message which is just the XOR of two plaintexts. If he knows one of the plaintexts or pieces of one of the plaintexts, he trivially gets the corresponding piece of the other, right? It turns out, using techniques developed long ago, back in the pre-commercial use of cryptography days, people knew how to, given only P1 XOR P2, basically extract both P1 and P2. Right? Now, mathematically, this is impossible because there are infinitely many solutions, but only a couple of them will have this piece of funny XOR be the XOR of two valid-looking messages. Right? English is highly redundant. If these two messages are English, what you do is you basically guess that the word the appears, say, here in the ciphertext. And you just totally guess. And then you work out what the plaintext would be for the other one. And if that looks like a plausible sequence of 3 letters in English, then you try to figure out what the previous letter probably is, and then work out the previous letter of the other one, and so on. And this is called this sliding pad. Sliding crib, rather. And you can basically work out what P1 and P2 are from P1 XOR P2. But of course, if you know one of them, you get the other one for free with no work at all. So what does WEP do? So we don't want to use the same key stream twice, right? So the key stream for WEP is RC4 of V comma K. And this depends only on V and K, right? If I use the same value of V and K again, I'm going to get the same key stream, and that would be bad, right, as we just saw. So, but K is fixed. Right? Everyone's using the same K, or at least you're using the same K for the duration of your session. Right? Even the products which allow key distribution with a different key for every person tend to use the same K for a while. Some of them do change them pretty often, and that helps somewhat. But let's say for now K is fixed for some amount of time, and possibly for some amount of users. Now the key stream depends only on V. So if you ever use the same value of V twice, you generate the same key stream. If two packets get transmitted with the same value of V, you reuse the key stream, which, as we said, is bad in big red letters. Also, as we saw in the diagram, V gets transmitted in the clear at the beginning of every packet. So the adversary knows when two packets have the same value of V, right? They're tagged at the beginning with the value of V they use. So all he has to do is keep this like table and just remember which values of V he's seen, and when he sees a value of V for the second time, then he can decrypt both of those packets. So how many possible values of V are there? How likely is it that you're going to see a repeat? Well, it turns out in the spec, they allocated 24 bits in the header for the value of V. Okay? So there are only 2 to the power of 24, or about 16 million possible values of V. Now 16 million is a big number for me to count up to, but my nice P3 here can do it pretty quick, right? So after 16 million packets, you have to repeat one due to a great mathematical result called the pigeonhole principle. Really, it's called the pigeonhole principle. So you're going to have to repeat one pretty quick. Oops. But wait, it gets worse. Okay? You only have to wait for 16 million if the adversary finds the worst possible thing happens, which is that he waits for 16 million packets and every one of them is different. Turns out, all the 802.11 cards we checked, every time you put the card in, it resets its IV to 0 and just increments by 1 for each packet it sends. So if I watch you send some traffic, and then tomorrow I come back and you boot up your computer again and send some more traffic, your IV space will overlap. They'll both be basically low numbers. And if you're using the same value of k, you've just repeated a whole lot of keystream. And now I can decrypt all your traffic. Also, in many installations, both directions from laptop to base station and base station to laptop use the same value of k. So that's another place we can get collisions. We can try to find when the laptop sends a value x and the base station sends a value x back. That's a collision that we can use. And also, if many different people are using the same k, I can try to find collisions between them. So if two people stick their cards in around the same time, they'll be colliding almost every packet they send. This makes collisions much more common. So what does the attacker do? So now we're going to play attacker, which is a much more fun thing to play. We have the decryption dictionary, which is the adversary knows both the ciphertext and the plain text for some packets encrypted with an IVV. And how can he arrange that? How can he arrange to know the plain text of certain packets? Well, it's actually pretty easy. He can, for example, send it to you, right? And how can he send it to you? He can ping you, right? If the wireless network is addressable from the outside, for example, he can just send a ping to your laptop with a large body. You know that pings can have arbitrary, well, not arbitrary, but some large amount of data in them. And he just fills that with a known pattern, say all zeros, and then sends it to you and looks at the encrypted result. And the encrypted result will just be the XOR of what he sent you with the pad RC4 K, V, and he just stores that. So for every value of V he sees, he just stores what the pad is. He still doesn't know K, right? Nowhere in here are we actually going to break RC4 and determine what the key K is. But we don't need to decrypt the data. We only need to know what the key stream generated by K and any IV we're likely to see is going to be. So we just generate this big table where each table is the size of a packet, which is 1.5 K, each entry. And how many entries are there? Well, at most 2 to the 24 of them. So this is a 24 gigabyte table. And if you go out to a store now and buy a 24 gigabyte minuscule hard drive, I mean, this costs you what, $100 today? 150? Not very expensive to buy a 24 gigabyte hard drive. So the attacker now has this big table that it's indexed by IV, and its value is this 1.5K pad, which is the result of the RC4 cipher. And then when he gets a packet that has a V that's in the table, he just looks up the pad, XORs the pad against the packet, and gets the clear text. Right? No key needed. The size of the table, another point, only depends on the number of IVs you're likely to see. It's independent of the size of K. Right? Whether you're using the 40-bit version or the 104-bit version doesn't matter at all to this attack. This attack doesn't know how big K is, it doesn't care. It only depends on how big the IV space is. And that's why having only a 24-bit IV really hurts you. If you had a much longer IV, this attack would not be possible. You wouldn't be able to store 2 to the 128 different table entries. Also, if you're using cards with the IV reset to 0 problem, then most IVs will be small, and the dictionary will be even smaller. You might only have to store several thousand IVs, starting with 0 and working your way up, rather than all 16 million. So, are there any questions up to this point? In the back? Yeah, we did. Yeah, the question was, has anyone actually prototyped this scenario? And we did in fact do it. We've done this in the lab where we built, we didn't build the entire 24 gigabyte dictionary, but we built enough entries that it was clear that this would just work if we wanted to just keep listening. Okay, I'll go on. So now I'll talk about message authentication. So far we've seen how an attacker can read packets going over the air. Message authentication, once again, if we think about how the WEP receiver works, the receiver will accept a packet if, after the decryption, the last 4 bytes of the plain text, the checksum is only a 4-byte number, is the correct checksum of the rest of it. So it decrypts the encrypted message, treats that as a message with 4 bytes of checksum, and calculates the checksum on the message part and sees if it matches the transmitted checksum. And if it does, that's how the receiver, quote, knows that the message was valid. So the checksum algorithm, we need to know what it is. It turns out it's CRC32. It's a very common checksum algorithm used in both wired and radio applications to prevent against random bit errors caused by noise. Right? It very efficiently can detect random errors in the transmitted stream. Turns out it's quite a poor choice for this protocol because while they're very good at detecting random errors, they're exceedingly poor at detecting malicious errors. It's very easy to create a new message whose CRC checksum is either the same as an existing one or has any given value you want. CRCs are not what in the literature we call one-way or collision resistant. Right? They're not secure hashes. They're useful against random mistakes, but not against a hacker with a pocket calculator. And it's weird that they put it here because there's already a CRC in the protocol. Right? At a lower layer than WEP, at the hardware transmission layer, there's already a CRC there. So they're already protecting against random errors. Right? So this CRC really is there to protect against malicious errors. But it doesn't. And we'll see why in just a second. So CRC32 has 2 main properties of importance. The first is that it is independent of the shared secret and the IV. If I take the same message, I'll get the same CRC out, even if I change the IV, even if I change the key. Right? This means that the attacker, even if he doesn't know the key or IV, can calculate correct CRCs for any message he wants. Okay, so that's property 1. Property 2 is a property called linearity. CRC is linear. This is where the technical knob pumps up another notch or 2. So this is kind of important to understand here for the next couple slides. So if I have a message M and I have a difference D, then if I create the new message, which is M XORed with D, so say D is just you flip 1 bit somewhere. So D is 00001, 0000, right? Then M XOR D is the same message as M, except one of the bits is flipped. Then the checksum on that message is just the checksum on the original message XORed with the checksum on the difference. So if I want to figure out what the checksum on the modified message is, even if I don't know the original message, but I know the checksum of the original message, well, I just calculate the checksum of the difference, which is 0001, 0000, which of course I can do because it doesn't depend on the shared secret, and then XOR that checksum with the original checksum, and I get the checksum of the modified message. Okay? So this checksum is very malleable. If we were to use something like SHA-1 or something, then you wouldn't be able to do this. If you only know what the difference between two messages is, you shouldn't be able to know anything about the difference between their SHA hashes or any secure hash. But CRC does not have this property. So this leads to an easy message modification attack. Suppose there's a message going over the air, and I want to change it. I don't know even maybe what it is, but I know I want to change a few particular bits in a particular way. Okay, so I have some D of my choosing, I'm the attacker, and I want to trick the receiver to accept the message F, which is our fake message, instead of the original message M. And F is M XOR D. So suppose the original transmitter sent the message M, which produced the ciphertext C after you XORed it with the right key, which I don't know, and the IV, V, which I do know because it's in the packet. So what do I do? Well, CRC32 is linear, as I said, and RC4, like all stream ciphers, is linear. And what do I mean by that? Well, very similar thing. If I know the RC4 encryption of a certain message, and I know the difference the change I want to make to that message, D, then all I do is take the original message, XOR in D. I don't even have to take the RC4 of D, which is good because I don't know the key. I can't do that. I just XOR in D to the ciphertext, and when the receiver decrypts it, he'll get the modified plaintext, just like I want, because of all this nice associativity and commutativity of XOR. The D's can just move around. So that's nice. So what do? The adversary takes the ciphertext C that was transmitted by the original sender, XORs in what? This thing which is D, the change I want to make to the message, followed by the checksum of D, the checksum of the change. So I just take that string and XOR it in with the original ciphertext to get a new ciphertext C prime, and just send the same V and C prime to the receiver. Okay? What does the receiver do? Here's another notch up because we have lots of green in this slide. So, okay, what does the receiver do? He has C prime. Now, when he wants to accept a packet, the algorithm is you find the RC4 key stream of V comma K. You XOR it in with C. So what was C? C prime. C prime was just C XOR D comma C of D, XOR RC4 of this. But C XOR RC4 of V comma K is just the original message, M comma C of M. So now we have M comma C of M XORed with D comma C of D. So all that means is you XOR the first bits and you XOR the second bits, and you have that the first part of this message is the original message XORed with the difference we want to make to it. The second part of the message is the checksum on the original message XORed with the checksum of the change we want to make to it. But this, by the property of linearity of CRC, is just the checksum on the modified message, and since F by definition is M XOR D, this is just F comma C of F. Okay, so this is a correctly formed decrypted message. So this seems a little weird. You shouldn't be able to do this. What I had was a message with a checksum on it, wrapped up in an encryption. I took this sealed envelope of encryption, I made some modifications to it without being able to open it, yet when it was opened, I got a different message with a valid checksum. Okay? It's not me, it's the math. Okay, so that shouldn't happen, right? You should never be able, you should not be able to, you should not design, you should be able to, but you shouldn't design a protocol where this is able to be the case. So what does the adversary do now? He checks that the checksum in the packet is in fact the correct checksum of the rest of the message, which it is. They're both C of F, except the message F is the one transmitted. The adversary has succeeded. Yeah. Okay. Right.
When the receiver opens up that envelope,
right.
Is that going to be something that's usable?
Yeah, well, it would be whatever message the sender, it's not like in a, for example, in a block cipher. If you change one bit of the ciphertext, it basically scrambles the whole block in some unpredictable way. With a stream cipher, if you change one bit of the ciphertext, it changes exactly that same bit in the plaintext. So let's say the attacker knows that this message is a funds transfer, right? And he knows that it's going to have a certain kind of header style and this, and he just wants to change the dollar amount by XORing in a certain value into that field. So all he does is takes that XORed value, call it D, calculates the checksum on D, C of D, and XORs this into the packet that was transmitted and then sends it on its merry way. The receiver will open it up and he'll find a message which is just the original message XORed with the change, that is the modified message the attacker wanted to send, which is a perfectly valid message, along with a valid checksum on it. There's no random scrambling that goes on here.
Right, but your example of it being, say, a funds transfer, the new modified message, what I'm saying is, would it still look like a funds transfer?
Yeah, absolutely. It'll look like anything the attacker wants it to look like. The attacker has great control here. He can make bit-level changes to the message for arbitrary bits of his choice. Yeah, it's a very powerful.
Testing. Test. Testing 1 2 1 2. Test.
Okay. The attacker jams the signal during the second half of the packet, but remembers what the first half was, and then the receiver fails because he only got half a packet. The attacker retransmits. The attacker now jams during the first half of the packet. So he sees the second half of the packet, and the receiver fails again. And now the attacker knows the whole packet, makes a modification, and transmits. Okay, so you can do things like that in order to prevent a packet from getting through. But as I said, in not all instances is it necessary even to prevent packets from getting through. Sometimes it's okay if the original goes through as well. Because remember that D can be an arbitrary change, right? It can change one packet to a completely different packet, right? As long as I have some idea of what the original packet looked like and I have some change I want to make to it. In the best case for the attacker, he knows the original packet, the contents of the original packet, say again because he sent it in a ping or something like this. If he knows the original packet, well, he can just modify it to be any packet he likes, right? It can be an arbitrary IP packet. And then he just sends that. So it's no problem that both the original and the modified packet went through in that event. Yep?
In more practical, even getting more practical than that question, let's say, talking about a person trying to do some kind of a trade or fund transfer from their call back to some server, and let's say they want to do something that involves $100. The attacker wants to change that, say, to $900. So they change that one bit that is the hundreds digit to a 9. Then the server, wouldn't it just send back a thing that says, are you sure you want it transferred to $900? Then the person would see that that was the problem.
Well, the attacker could change the one coming back too. Right. So, but that's an application level issue, right? The application level had the confirmation thing in there. So, I mean, one way to hack it is, as I said, just change the query and change the confirmation. But certainly some protocols don't do that sort of thing, and they're just one shot off. Yep.
You tested this like with a replay session where you could basically generate the table yourself and come back later and blind so you can do the next session.
So as I said, we generated part of a table, but we didn't generate the entire table. So
What I meant is so that way you wouldn't actually have to be intercepting packets. You could just blast through. If you wanted to go buy something for $0, have it shipped to you, but if you want something for the entire session, you could do the whole thing.
oh, it turns out if you just want to insert packets, which I'll get to in a moment, you don't need to know the entire table. You only need to know one entry in the table. So, yes. So I'll get to that in just this slide here. So message injection. So what happens if you want to just insert traffic into the network and just make it look like it came from the person you want to spoof, but it can have any contents you want. So let's say the attacker wants to generate a fake message M, completely of his choice, into the wireless net, so that will be received as genuine. And let's say the attacker knows a single plain text and its corresponding encrypted packet. Okay, so he knows just a single line in that table. And again, how did he do this? He could have sent a ping through the network. He could have sent spam. Turns out there are other easier ways even, which I'll show you shortly. The encrypted packet then is just V, C. He gets the entry for the table, which is the plain text XORed with the ciphertext, which is just the key stream. And now he just wants to transmit any fake packet of his choosing. He takes F, computes C of F, which he knows how to do because C, again, doesn't depend on the key. And then just takes F, C of F, XORs in the key stream from the table using the same value of V and transmits V, C prime. And what does the receiver do? The receiver decrypts the packet using the same key stream the attacker used, but it's a correct encryption, so the receiver has no reason to reject it. So the adversary has succeeded once again. So the only thing we used here was the fact that the CRC does not depend on the key. We didn't use the fact that it was linear, right? This attack would work equally well if the checksum was something cryptographically strong, like SHA-1, right? Which is a little counterintuitive, but even if we used a perfectly good cryptographically strong hash function, this would not protect this attack. That's because what we need in this attack is a message authentication code, not a hash function. And if you use cryptographic primitives where they don't belong, as my office mate Dave used to say, your warranty is void. Right? You don't get the cryptographic properties you want if you use things you aren't supposed to use. So we needed to know a single plaintext ciphertext pair. So, as I said, we could send pings if it's connected to the outside world. We could send spam if it's connected to the outside world. Well, if it's not connected to the outside world, it's just a local network, not connected to the internet at all, right? I'm sure there are lots of wireless networks like that. How can we get a plaintext ciphertext pair? Turns out, the authentication protocol of 802.11 gives it to the adversary for free. All right, this is a major disaster in the design. Okay? The authentication protocol, which I'll describe in a moment, it's supposed to prove that a certain client knows the shared secret K. But the way it's set up is, if I watch you prove to the server that you know K, then I can just repeat the proof to the server, even without knowing K. So it's kind of like the what's the password protocol, right? If I watch you prove that you know a certain password by saying the password, then I learn the password too. Okay, this is a little bit trickier because I never do learn K, so the math is one line extra, in that I never do learn what K is, because the protocol isn't, oh, what's K, and you tell him what K is. I'll show you the protocol in a minute, but it's of the same form, that if I ever watch you do it, then I can then do it forever on, as long as the key doesn't change. So that's pretty bad. Yeah. So it gives you, correct, that's a good observation, which I didn't address in these slides for interest of time. It does give you only a small piece of the pad. Turns out there's something called the pad extension attack, which uses the fact that in the protocol M, C of M, the length of M is never encoded. So if you just truncate a packet anywhere, the receiver will just treat the last 4 bytes as the checksum and the rest of it as the message. So the truncation of a long pad is a correct short pad. If you have a correct short pad, turns out it's relatively easy to extend it. What you do is basically just guess what the next byte is, and send 256 packets, each with one guess, to the server, and he'll accept one of them. Okay? This is pretty easy. And then you just keep doing this. So from a single short pad, you can build up a long pad by sending 256 times the number of bytes you're missing, packets. But you only have to do it once, right? So it takes some time to extend a short pad to a long pad, but it's easy. Good question, though. Anything else? Okay, I'll go on. So here's how the authentication protocol works. The base station, the client says, ooh, I'm a client. And the base station says, prove to me you know the WEP secret. Here is a challenge. Send it back to me encrypted. And the client says, okay, and he encrypts the challenge and sends it back. So now you've just seen a plain text. So the base station will check that the challenge is correctly encrypted, and if so, accepts the client. But the adversary has just seen both the plain text and the ciphertext of this challenge, right? So this is enough to inject packets. In the previous attack, he only needed to know one plain text ciphertext pair. But he can also execute the authentication protocol, right? So authentication spoofing. Once the adversary has seen a single execution of the protocol, he can extract V and the pad, and now he tries to connect to the network himself. The base station sends a challenge string. The adversary just takes M, C of, or M prime, C of M prime, where M prime is the challenge string, XORs it with the pad that he extracted from the authentication success that he saw, and transmits it. And this is the correct response, so the base station has no way of distinguishing him from someone who's validly on the network. So the adversary, again, has succeeded, even though he never did learn the value of K. So now we're going to come to some other surprising bits. It turns out the ability to modify and inject packets also leads to ways the adversary can decrypt packets. So the 802.11 designers sometimes come out and say, yeah, well, we didn't really mean it as goals of the protocol to prevent modification and injection. We only meant it to prevent eavesdropping, right? So they admit that they bumbled up a bit for the first kind of attack where the IV was too short, and you could build the dictionary or watch for collisions or things like this. But they say, well, but this other stuff about injecting, that's not really a problem because we were never supposed to defend against it. You did say it was wired equivalent, right? You can't, and remote adversary can't inject packets on your physical wire. I don't think he should be able to inject it on the air, but they claim, well, we didn't really mean it. Turns out, even if you fix the first part, that is, you make a long IV, but you still allow these modifications and injections, we still have ways for the adversary to read your data. And here's how we do that. So the adversary can't decrypt the packets himself because he doesn't know K, the shared secret. And RC4 is a strong cipher, so he's not going to be able to break the crypto. So he has to basically, if he wants to decrypt it, he has to get someone who knows the plaintext to tell it to him, right? Or someone who knows the key to perform the decryption for him. So who knows that? The client knows that, and the base station knows that. 2 people know K, or maybe lots of people know K in the case where we have 1,000 people. But what we're going to do is have the adversary trick the base station into decrypting the packet for him and telling him the result. Okay? So this is going to be fun. So it turns out there are at least 3 ways. I'm going to talk about 3 different ways to do this. They're called double encryption, IP redirection, and reaction attacks. So the first one, double encryption. So everyone flips over a page. I must have just. So double encryption. As with all stream ciphers, when you decrypt, it's the same as when you encrypt, right? You just XOR the pad against the message. So if you do it twice, if you encrypt the same message, or if you, encrypt a message with a key and encrypt that result again with the same key, you'll get the original message back. It's like double ROT13, right? It's very much like double ROT13. So if the adversary wants a certain packet decrypted, so he's intercepted this packet and he'd really like to know what it says, say he can tell just from the traffic analysis that this is an HTTP request which contains a post which contains a password, say. So he has one particular packet which he would really like decrypted. So he joins the network using authentication spoofing, which we saw how to do. He uses a second internet connection to send the packet to his laptop over the wireless network, okay? So he's sitting there with his laptop here at the thing and starts a TCP session with some other machine he owns somewhere on the network, and then takes this encrypted packet and sends the encrypted packet as plain text to his laptop's wireless address over the internet from the other machine he owns. Okay? So now this packet is going to arrive at his laptop, and while it's over the air, it will be encrypted again. But it's already encrypted. So if he can arrange that it's encrypted again with the same key stream, then if he uses a radio to watch over the air, he'll see the original decrypted message. Right? Pretty slick. So the trick is you have to use the same IV to get the same key stream to encrypt the message the second time. So this is where you use the fact that most cards just sequentially increment the IVs. So you just watch for the base station's IV that it's transmitting, and when it gets close, you just send 100 copies to yourself and just grab the one that has the right IV in it, which is indicated in the header. So it's not very hard at all. And you just read the decrypted packet off the air. Note that the adversary's card can't actually decrypt the packet because it doesn't actually know K. Right? So you have to listen with hardware on the air. Okay, so that's one way to do it. Here's another way which avoids that funny timing issue and also works if the base station isn't just sequentially incrementing IVs. So that's not a requirement for these attacks. So again, join the network with authentication spoofing. You take the packet to decrypt and modify it using the message modification techniques we used before so that the IP address of the packet instead of being to whatever web server it was originally, is your machine somewhere on the internet, right? So I have this packet that I don't know what it says in the body, but I know what the IP header looks like, right? Because I know what machine this guy was trying to connect to. And so I can take the IP destination field, whose original value I know, and modify it so it's now pointing to a machine I control, and transmit that instead, right? Or just retransmit that. And here's a case where I don't need to block the original packet. I just need to send the new modified one. And now the internet will happily route that packet to my machine after the base station has decrypted it. So woohoo. There's an issue with getting the IP header checksum right, because when you modify the IP destination field, you'll have to also modify the IP checksum. But it turns out that's pretty easy to do. And in the paper where we talk about this, which you can find on the website, which I'll point you to at the end, there's a pretty detailed section about how to correct the IP, how to correct for the IP destinations change in the checksum. Even if there's a firewall, you can play other IP header games, right? You can change the port number, you can change the TCP flags, you can change whatever you want to make it look like a packet that ought to go through the firewall in that direction, right? So you can turn off the SYNs and turn on the ACKs and make sure that this looks just like the middle part of some age-old connection or a current connection, right? You're connected to the net, you can pretend to have a connection out there, the firewall, the stateful firewall starts one up. I mean, also, you can use your imagination here. And the third kind of attack we can use is called a reaction attack. And this is a particularly insidious kind of attack, because here, this works even if the wireless network isn't connected to the internet at all. So there's no, in the previous two attacks, we needed this second channel, right, that doesn't go over the wireless network, that can connect to the wireless network, or that packets from the wireless network can get to. In this attack, we don't need any such thing. We just need that there's, for example, the original person sent an HTTP request to some maybe internal machine, right, and had a password, and you wanted to know what that password is. And it's some internal machine sitting on the network. So here's what we're going to do. We'll use the fact that TCP has a checksum, right, which incorporates, unlike, so the IP checksum just checks the header. The TCP checksum also checks the data, okay? So TCP has a checksum. What we're going to do is modify the packet in such a way that we're going to basically guess each bit of the packet, whether it's 1 or 0. And we're going to do it in such a way that if we guess right, then the TCP checksum of the modified packet will be correct. And when we retransmit that modified packet, the TCP checksum is correct even though the data is wrong, and we'll get a reset or an ACK back or something, right? Because it's a valid TCP packet, and the destination machine's gonna respond somehow, usually with a reset, if it's a closed connection, or with an ACK if it's still part of the old open connection. So if I see you send the packet, and while that TCP connection's still open, I retransmit it with 1 bit different, or guessing at 1 bit with a slightly different TCP checksum, if the checksum's correct, you'll get an ACK back. And I won't be able to read the ACK because it's encrypted, but I'll see the packet. If I guess wrong, and the TCP checksum is now incorrect, the packet will be silently dropped. That's how TCP stacks generally work. So even though we never ever see the result of decrypting this packet, we use the fact that the destination machine does see it, and will have different behavior, different reactions, depending on whether we guessed correctly or incorrectly on the value of any particular bit in the message. So we just do this, send 1 packet for every bit in the message that we want to decrypt. So let's say I know the password is here, or likely to be around here somewhere. Then I just take those, passwords are like 8 characters, so, and I know the top bits are probably 0. So I just have to send 56 packets to the server and watch which ones get a TCP acknowledged and which ones don't, and that tells me which ones I guessed right and which ones I guessed wrong, and that tells me what the bits were. And the details of this are pretty interesting. It uses the fact that there are now 2 checksums in the message. There's the CRC checksum, which is linear with relation to XOR. So the checksum of A XOR B is the checksum of A XOR the checksum of B. And there's the TCP checksum, which is linear with respect to addition mod 65535. Right? Here's another notch up on the technical. So we have 2 checksums which are slightly different. If I make a change to the data, then I have to make 2 slightly different changes to the checksums. Sometimes, it turns out addition and XOR agree a lot some of the time and differ other times. And that's using that difference, we know that if the TCP checksum agreed, then we know, say, the bit was 0, and if it disagreed, we know the bit was 1. And that's the trick we use. Okay, so this is sounding pretty bad. Yeah, question? No, K is the key, not the key stream. K, so I did use capital K somewhat poorly in a couple of slides to represent the key stream, but lowercase k is the input to RC4, which, since RC4 is presumed to be a strong cipher, even if we know the key stream, you don't get the key, the shared secret out. And also, in at least this attack, the reaction attack, we never do see the decrypted message. Right, we only see the reaction to the decrypted message. But in the previous 2 attacks, we do, in fact, see both the encrypted and the decrypted form. Any other questions on the attacks? So the question is, we know RC4 is a publicly known algorithm. We know the length of the key. If we know the key stream, could we not brute force what the key is? And the answer is, well, you could try. And if you're only using the 40-bit version, then yes, you can. If you're using the 40-bit version, then all you need is 1 packet that you know both the plaintext and ciphertext of, and then just brute force what K is, and now you're totally done because you know the secret. Right? That's why you should never use 40-bit crypto, right? I thought we learned this years and years ago, but oh well. So they're using 104-bit crypto. So you could try to brute force it. It'll take you 2 to the 104 guesses, which is a long, long, long time. We consider that well into the unbrutable range. Yeah? You're sending it, you don't care, right? Because you want to send it to yourself. You don't want this modified TCP packet to be actually treated as part of the same session. So in fact, you do want the ISN to stay the same so that the remote stack will ignore it. It'll think, oh, this is just old retransmitted data that has been sitting around in the internet for an hour somehow. Yeah. TTL, decrement your TTL when seconds elapse. Right, you want the receiving stack to ignore the message, so you want to keep the ISN the same. But of course, if you wanted to change it, we know how to modify data, right? We could just modify it at will. That's in the attack, that's in the message reaction attack. And the other attacks, like the IP redirection, where we change it to point to us, we don't care what the ISN is, because we're not going to actually start a TCP session with this packet. We're just going to read it off the net and never feed it to our TCP stack. right? We're just treating the whole packet as arbitrary data that gets sent over the internet. Okay, it's actually hard to see hands in the sea of people, so I hope I'm not, yeah? Do I have to license it? Well, depends who you ask, right? If you ask the RSA, they'll say, of course you do. But they might be. It turns out, as far as I'm aware, there is no legal reason to pay RSA to provide RC4. It's not a patented algorithm. The name is trademarked, so if you want to call it RC4, you have to do something special, but that's easy to avoid, right? Just use a different language or something. Yeah?
Do you have any clue why there's no entropy in the system? No hardware entropy?
Well, that's actually an independent and orthogonal point to the design. Where you would use the entropy is in picking K and picking V. Well, K, we assume it's picked once and fixed. So for all we know, is picked with a big jug of billiard balls and you pick them out like in a lottery, right? Because it's done once and then someone just types it into everyone's computer. V, of course, is picked for every packet. They could be generated randomly. It turns out that's worse. And the reason it's worse has to do with what's called the birthday paradox, which I'm sure you're all familiar with. If we take like these 23 people here, odds are 50-50 that two of them will have the same birthday. So if you picked random V's every time, then after only about 4,000 packets will you expect two of them to collide. Whereas the correct thing is pick a random starting point and then for every packet increment, right? That is technically the most correct thing to do, and you want to make the space really big so you don't wrap. Okay, so I'll go on to countermeasures. So what can we do? So now let's take off our black hats and go to another conference. And now we put on the hats of, so we're the admins, we have this WEP network. We've just seen these slides, and we know all these black hat people have seen these slides and are now about to go war driving with WEP-equipped breakers, right? So what can we do? The easiest thing, I think, is just don't assume it's secure, right? You have this wireless network. It has this wired equivalent protocol for security. I say just ignore it, right? I mean, turn it on if you want, like belt and suspenders is always good, but don't rely on it for security. Treat the wireless network like a public network, right? Pretend anyone has complete access to this network, just like the rest of the internet. So where do you put the rest of the internet in relation to your company? There's a big wall between you and them. Put your wireless network on the other side of that wall. Right. The wireless network should be outside your firewall. In order for your employees who are using this wireless network to connect to internal machines, they should have to use whatever mechanism they use today to connect from home. SSH, IPsec, VPN, whatever. Right? You can even hook it up so that, I mean, probably the right thing to do is make the wireless network not routable to anything except your firewall, right? So you can't just join the wireless network and then connect to the internet directly, right? The only machine you should be able to connect to is the firewall, and you have to authenticate yourself to the firewall using whatever VPN tools you use today. And that way, an attacker who can get on the network is in exactly the same position as if he were on a wired network trying to get through your firewall, which hopefully you've paid good money to you people to make sure that can't happen. Right, so another point which I made earlier, it's not enough. So after we published this paper, we got a lot of queries of the form, oh, such and such a company has a better key management product for 802.11x. Have you looked at it and is it more secure? And the answer is, it doesn't matter. That's not where the problem is. right? I don't care if every user of your company automatically gets a different shared secret every time he logs in, right? I can use, as long as he keeps the same secret for a little while, I can use the attacks I described earlier to insert packets on the net, modify packets, decrypt packets. So yes, it's useful to do this, and it solves other problems like 1,000 people knowing the same secret, but it's not sufficient. So this previous slide describes what to do in an existing system to facilitate the use of WEP, even without having to go change the protocol or hardware or stuff. This is just reconfiguring what gets plugged into what. So now, let's say you're on the WEP standardization committee. Okay, what should you do to fix this? So let's say we want to change WEP, and they are. And unfortunately, the current standard, so we need both. Let me just talk about this first, and then I'll talk about the current state. We need two things. To fix the two-time pad and similar message decryption attacks, you need longer IVs than 24 bits, right? These long IVs have to be guaranteed to never repeat for the lifetime of a shared secret and never be duplicated if more than one machine shares the same secret. Okay? This is a bit tricky to get right. How do you know, let's say the 5 of us use the same value of k, how can we guarantee that I never use the same value of v that you use? And it's a bit tricky to get that right, but you can do it. Even more insidious, let's say I'm talking to a base station and we're using the same k for both directions. How do we guarantee that neither of us ever uses a v that the other guy used? So there are those issues to be solved. Turns out it's relatively straightforward for someone with cryptographic training to do that. The second thing you need is a strong message authentication code instead of the CRC. So this message authentication code has to have the properties of collision resistance, one way. It might not need exactly those strong properties, but you may as well use them. And it has to depend on the key in the IV, right? Not depending on the key in the IV was a mistake we saw earlier for message injection, for example, where even if you used a strong cryptographic hash, which is basically a keyless MAC, then you still have problems. So we need a strong message authentication code such as SHA-1H MAC, right? Or something like that, or CBC MAC, or there are lots of them. And this, as a side effect, will fix the problem in the authentication protocol, right? The authentication protocol had that problem with, here's a message, show me the encrypted version of it. If there's a strong MAC, then if I see the encrypted version of one message, then it doesn't help me figure out what the encrypted version of a second message is. Just doing one of these doesn't fix the problems, right? Even if, so, and this brings us to the current state of WEP. So WEP is currently doing a couple things. It's deploying an interim short-term fix, which is basically just fixing the first one. Okay, it's making the ability to have longer IVs. But as we said, that helps almost not at all, right? But it's something, right? In addition to that, they're working on a longer-term fix to actually get it right. And it turns out there are some political issues involved with things like I said earlier, where some people are saying, oh, well, we're not really guaranteeing things about authenticity or integrity or modification, things like that, or injection. We just want to protect about decryption, and so we shouldn't have to bother with this strong HMAC thing. But now that this is coming out, people are pointing and saying, no, no, no. Even to get protection against decryption, you still have to do strong authentication, so you may as well do it anyway. So what are the lessons we've learned about WEP? The first one, designing security protocols is hard. You thought designing crypto algorithms was hard? So is this. I would say this is sometimes harder. Even when you use the right primitives, right? We used RC4. It's not like we made up a cipher, made up a stream cipher that was like grad student level to break. We're not going to break RC4 in order to break this. We're going to go around it, right? In almost every system today with good crypto, you don't break the crypto, you go around the crypto. And the way we go around the crypto was we got other devices to do the crypto for us. We used the fact that if we encrypt two different messages with the same key, then we'll get related ciphertexts and things like this. So the simple advice in designing protocols is just don't do it, right? Just like the advice in designing a crypto algorithm is don't do it, use an existing good one, same thing here. So the first lesson is to reuse old designs where possible. At least look at them, right? If you're not going to just pick up an old protocol that someone has designed and is using today, at least look at it, look at its design decisions, and learn from it. A lot of you might remember the paper Breaking PPTP that was, I don't know, a few years back, Mudge and Bruce put together. That had a lot of these very same problems, right? Identical problems were in PPTP as are in WEP. You'd think these people would have looked at it and noticed that and not made the same mistake again, right? We can forgive you for making a mistake. It's hard to forgive you for making a mistake again. IPsec also had a lot of the same issues during its design phase. The second thing is make the design process public and inviting. You explicitly need to find experts, crypto, security, protocol experts, to come look at it. The CRC is linear problem, for example, that allowed easy modification would have been spotted right away by someone who has had any kind of stream cipher protocol background. The problem with the IEEE process is that it is technically open, right? Anyone can join an IEEE working group. So they just kind of assume that cryptographers will do this, right? And they don't make special effort and just assume that someone on this working group must have taken a look at the security thing and given its blessing, but apparently no one did. So that's not so good. The other thing was, until recently, IEEE specs were really hard to get. You had to pay a lot of money for them, which is, again, not encouraging for people who want to look at them. It turned out that the way we got involved in this is that some other group at Berkeley needed to buy the IEEE 802.11 spec for some totally other reason, just involving wireless networking and nothing to do with security. But while it was in the office, we went, hey, let's take a look at the security of this thing. And so we did, and so this is the result. Now, however, the 802 working group has decided in all wisdom, and it's very clever, to just put them up on the internet. This internet thing's going to rock. I mean, it's going to be huge. So now, luckily, you can just get the protocols. So, just to wrap up, conclusions. We've demonstrated attacks on the wired equivalent privacy protocol that defeat each of the security goals of confidentiality. We can read the traffic, access control. We can inject traffic, data integrity. We can modify traffic. This doesn't kill wireless Ethernet, right? You can still use your wireless Ethernet just as you were doing before. You just have to assume it's not secure and use other security mechanisms like SSH or a VPN or IPsec or something on top of your wireless net. I'm sure a lot of you are using the wireless net here with SSH on top of it, yes? Yeah. So that's certainly something you can do today. We don't have to throw out this great wireless hardware. Open standards are more likely to be secure. They're not, I didn't say open standards are more secure, right? Because just because it's open doesn't mean anyone actually looked at it. But it helps. And mumble GSM mumble for an example of the contrapositive. For more information describing these attacks, we have a URL here, www.isaaccsberkeley.edu/isaac/wep-fact.html. And that has links to a bunch of things, including a preprint of the paper with a lot of details, and wired equivalent privacy isn't. So that's all I have.